Okay, hi everybody. My name is Shakib Mehri, and today I'm excited to talk about our work on LAD, Language Models as Data for Zero-Shot Dialogue. This work was done with Yasmin and Maxine Eskenazi, my advisor. Generalizing to unseen tasks and domains without additional training data is a highly desired property of dialogue systems. Large language models have brought about significant progress in zero-shot and few-shot generalization across NLP. So why is zero-shot generalization and task-oriented dialogue still difficult? If a large language model can understand language, why does it struggle to classify intents or to detect slots? And similarly, if a large language model is capable of generating language, why does it struggle to complete dialogue tasks without additional training data? Our answer to this question is structural constraints. Structural constraints is a term that we introduce in this paper to conceptually define what a model must learn. The necessary structural constraints are implied by the problem, the domain, and the task. In intent prediction, the primary structural constraint is that utterances with the same intent should have similar representations. In slot filling, the primary constraint is that representations for contiguous spans of text should be similar if the corresponding slots being communicated are the same. And in the problem of next action prediction, we have the structural constraints of intent prediction and slot detection. And in addition to this, we also have the constraint of the dialogue policy. A next action prediction model must learn to generate system actions according to a task-specific dialogue policy. Typically, structural constraints are learned by training on data. The more data you have, the better the structural constraints can be learned by a downstream neural model. In contrast, zero-shot generalization can be conceptualized as imposing the necessary structural constraints without any data. And so in order to design an effective approach for zero-shot generalization, it's imperative that we understand the necessary structural constraints, or in other words, what the model must learn. Task-oriented dialogue has structural constraints that large language models cannot know about a priori. While large language models exhibit strong NLU and strong NLG, in zero-shot settings, they do not and cannot have a priori knowledge of the necessary task-specific constraints. So even though a large language model may have really strong language understanding skills, there's no guarantee that its representation space is structured according to our specific domain ontology. And this is the reason that large language models can't be used off the shelf for zero-shot generalization in task-oriented dialogue. The primary goal of this work is to induce zero-shot generalization by leveraging the strengths of large language models, specifically GPT-3, as well as knowledge of the structural constraints. We address the three aforementioned dialogue tasks: intent prediction, slot filling, and next action prediction. So how are structural constraints generally learned? With moderately sized language models, such as BERT, we can learn the structural constraints during fine-tuning. Inductive biases in the model architecture or in the problem formulation can facilitate sample-efficient learning of these structural constraints. With large language models, the dominant approach for expressing the structural constraints is through the prompt. We can express the domain ontology or the dialogue policy through natural language instructions or few-shot examples in the prompt. However, with complex structural constraints, especially things like the dialogue policy, it is difficult to effectively convey the constraints in natural language and in the fixed length of the prompt. Furthermore, especially in academic settings, it's infeasible to fine-tune large language models. And large language models generally have immutable architectures and therefore preclude the use of inductive biases in the architecture. So basically, we have these multi-billion parameter language models, but it's non-trivial to leverage them for task-oriented dialogue because of the difficulty of imposing the necessary structural constraints on the model. Fine-tuning is impractical and prompting is often ineffective. So at this point, it should be clear that learning a task is equivalent to learning the necessary task-specific structural constraints. Zero-shot generalization is conceptualized as imposing the necessary structural constraints upon a model without any training data. But we can't do any of this without knowledge of the structural constraints. We can't expect any type of zero-shot generalization to a specific dialog setting without knowledge of the domain ontology or the dialog policy. To this end, we define a minimal expression of the structural constraints. This minimal expression, which we refer to as a schema, must convey all of the necessary task-specific structural constraints. And the claim that we're making here is that fundamentally, you cannot expect zero-shot generalization without at least having this minimal expression of the structural constraints. And what we hope to show in this paper is that the minimal expression is sufficient for facilitating generalization. So the information that the schema contains differs depending on the types of problems that we want to address, because the types of structural constraints differ depending on the problem. For intent prediction, the schema consists of one utterance per intent class. For slot filling, the schema must consist of one utterance per slot key, but then also a few example slot values. And for next action prediction, which requires intent prediction, slot detection, and action prediction, we need an utterance per intent, example slot values, and the task-specific policy graph, which must convey the task-specific policy. So now that we have defined a minimal expression of the structural constraints, we can begin to tackle the problem of imposing these constraints in a zero-shot manner. And we want to do so by leveraging the strengths of large language models. To this end, we introduce language models as data, or LAD. The key idea behind LAD is that we use large language models to induce linguistic diversity in synthetic data. Given a minimal expression of the structural constraints, a schema, LAD first creates a seed synthetic data set that expresses the structural constraints. However, this data is created with utterance templates and is too formulaic to actually use to train a model. So as such, we leverage GPT-3 to reformulate utterances and induce linguistic diversity in the synthetic data. We can then use the synthetic data to fine-tune our task-specific dialogue models, which are built on top of pre-trained models like BERT and have inductive biases that make them robust and sample efficient. In contrast to the dominant approach for using large language models, which is prompting, LAD uses structural constraints both to create synthetic data and to inform the design of inductive biases in the downstream models, which rely on smaller pre-trained models. LAD is not limited to expressing the structural constraints through natural language. And as such, LAD allows us to leverage the strengths of large language models to facilitate zero-shot generalization in a domain and problem agnostic manner. Here we visualize the process of creating diverse and accurate synthetic data with LAD. We begin with the schema, which, as I defined earlier, is a minimal expression of the structural constraints. As a reminder, for next action prediction, the schema will include a graph-based representation of the task-specific dialogue policy, a single utterance template for each intent, and a few example slot values for each slot type. We first create a seed dataset using domain-agnostic algorithms. For the problem of next action prediction, our algorithm for creating seed data randomly traverses the task-specific policy graph while also randomly combining user actions. In this manner, we can generate synthetic dialogues with diverse user behavior, but consistently deterministic system behavior. Once we've generated the seed dataset, we can leverage GPT-3 to reformulate utterances. This is possible due to the few-shot in-context learning abilities of large language models. In the prompt, we provide an instruction and a set of examples, and find that GPT-3 performs reasonably well at producing fluent and natural reformulated utterances without altering the original semantic meaning. Since GPT-3 may sometimes drop slots, we do leverage simple validation heuristics to filter out erroneous reformulations. Through these three steps, the seed data algorithm, the reformulation with GPT-3, and the validation heuristics, LAD is able to generate diverse and accurate synthetic data given only a schema, or a minimal expression of the task-specific structural constraints. A noteworthy aspect of LAD is the specific prompt that we choose to reformulate an utterance. Rather than generating one reformulation at a time, we explicitly instruct GPT-3 through both the instruction and the few-shot examples to generate 5 different reformulations. In this manner, we are inducing linguistic diversity both through the prompt and through the decoding algorithm used by GPT-3. So we use LAD to tackle 3 different problems. We select 5 different data sets across the 3 problems and create synthetic data with LAD that addresses the same dialogue domains and tasks. Here we show the size of each synthetic data set and the cost of using the GPT-3 API to create the data. And as you can see here, it's fairly reasonable to create these data sets. Here are example reformulations produced by LAD. The reformulations produced by LAD are linguistically diverse, but retain the original meaning of the utterance. I'll give you guys some time to look over this. And here's an example dialogue produced by LAD. To create this dialogue, we first randomly traversed the policy graph and constructed a seed dialogue. Each user utterance in the seed dialogue is a concatenation of template utterances for a randomly sampled set of user actions. So basically, for each user turn, we sample a bunch of different user actions, take their templates, and concatenate them. Given this concatenation of template utterances, we use GPT-3 to reformulate this and make it into a natural utterance. And GPT-3 is able to do this reformulation because of this assumption that large language models have learned something about the distributional structure of language. So the way we do our experiments is we select a strong downstream model to fine-tune for each one of the problems. For intent prediction, we leverage convert with example-driven training and observers. For slot filling, we use GenSF. And for next action prediction, we leverage the schema attention model, or SAM. We take each one of these models, which have inductive biases that make them robust and sample efficient, and we fine-tune these models on the synthetic data that is created by LAD. So these models have only seen data that was synthetically generated, and the data was generated conditioned on nothing but a schema. So this whole process of training a model, if you consider the data generation as part of the process of training a model, begins with a schema and gives you a trained model that understands the structural constraints. Once we have this trained model, we then evaluate them on the original human annotated test sets. Here we show the performance of one-shot intent prediction. Using LAD to create synthetic data results in a 15 to 20% improvement in accuracy across the 3 intent prediction data sets: HWU, Clink, and banking. This table shows the performance on zero-shot slot filling on the restaurant 8K corpus. LAD is able to create synthetic data for slot filling using only a single utterance template for each slot type. So the only human work that was done here was for each one of the 7 or 6 different slots in this data sets, I wrote a template utterance. So like the time of the restaurant reservation should be, and then slot value. This synthetic data after reformulation with GPT-3 is sufficiently diverse and accurate, and therefore results in a 30-point improvement over GenSF. Here we show the zero-shot performance for next action prediction on the star corpus. SAM zero-shot, which explicitly attends to the policy graphs, already achieves a fairly good score of 53.31. Training on the synthetic data produced by LAD results in an F1 of 64.36. And to clarify, the way that this experiment was done was the sample LAD model was trained on no human annotated dialogues whatsoever. It only saw data generated by LAD. And interestingly, this result is only 6 points lower than the performance of training on all of the human annotated training data. But our zero-shot performance on next action prediction leads us to question whether our evaluation is enough. How can you really validate the quality of different data sets? It's possible that our performance on the star test set is deceptively low because we're not modeling noise or arbitrary phenomena that's present in the human annotated data. So to this end, we perform an interactive human evaluation on Amazon Mechanical Turk. We basically have a worker interact with a dialogue model according to some scenario and ask them 3 different questions after the dialogue. We ask them whether the system completed the task, whether the system asked for all the necessary information, and whether the system asked for information that was already provided by the user. So we compared 3 different models. SAM zero-shot, which has been trained on human annotated data for every task except for the target task. SAM plus LAD, which has observed no human annotated data and has only been trained on synthetic data. and SAM full shot, which has been trained on all of the human annotated data. We collect at least 500 dialogues for each one of the systems, and the results here demonstrate that these three models are comparable on 2 of the 3 qualities. And SAM plus LAD is statistically significantly better on asking for all of the information. Through this interactive evaluation, we demonstrate that the synthetic data produced by LAD allows downstream models to effectively learn the necessary structural constraints and attain comparable performance in interactive settings. So to summarize, we demonstrate that LAD can create diverse and accurate synthetic data that effectively enforces the necessary task-specific structural constraints and thereby improves zero-shot generalization in Dialog. For one-shot intent prediction, we achieve 15 to 20% improvements across 3 different data sets. For zero-shot slot filling, LAD facilitates a 30-point improvement in the F1 score. And for the problem of next action prediction, we achieve an 11-point improvement in the F1 score. And finally, our interactive human evaluation shows that SAM plus LAD is comparable to the full shot SAM model and significantly better on asking for everything. So in this paper, we introduced LAD, which can create diverse and accurate synthetic data that is shown to effectively enforce the structural constraints and improve zero-shot generalization in Dialog. We empirically demonstrate that large language models can generate reformulations in a domain-agnostic manner. And finally, we provide an effective alternative to prompting, which allows us to leverage large language models for tasks with complex structural constraints. Future work can explore improving the reformulation step by using a better prompt, a better language model, or generating more reformulations than we did in this work. Future work could potentially explore improving the validation step. So LAD is incapable of detecting some errors in the reformulations, for example, hallucinations. And so some of the synthetic data will be noisy. This can potentially be improved by incorporating some type of classifier in the validation step of LAD. Future work could explore additional experiments, for example, assessing the impact of the prompt or the number of reformulations. And finally, LAD can be extended to other tasks and domains, such as open domain dialogue or response generation. Thank you for your attention, and you can find the paper and the code at these QR codes.
Any questions? Okay. Hello, Georgi from University of Cambridge. So first of all, great talk. I really enjoyed it. I was wondering, I might be a bit greedy, but you show that well, LAD plus the kind of the zero-shot baseline achieves good results, but not as good as the full-shot learning. I was wondering, have you tried full-shot learning plus the LAD data?
Yeah, that's a great question. I did try that. I didn't include those experiments in the paper, but I did both LAD plus few shot data and LAD plus full shot data and found that in neither of those settings, LAD helped. And I think the reason for this is because even though LAD generates data that expresses the structural constraints, it's still a subset of the structural constraints expressed by the full data. So unless we're generating reformulations conditioned on all of the way to do this, the way to apply LAD, in my opinion, to the few shot data or the full shot data and get improvements is to reformulate all of the few shot data. But if we're only reformulating condition on the schema, then that's not generating diverse enough data to really complement the original training sets.
All right, thank you.
Yeah, thanks.
Hello, Gabriel Skanse from KTH here. Thank you, very interesting talk. I have one question regarding this. It seems like you're doing these paraphrases without the dialogue context. So if you go back to slide 15, for example, you had an example. So what day would you like to make the booking for?
Yeah.
And you could answer just Wednesday there, right? How would you deal with rephrasing of utterances sort of that are more context dependent?
Well, we have full control over the original utterances that we're reformulating because they're produced by a template. But I do understand the concern that you're bringing up, and that is a legitimate problem if we ever want to take human data and reformulate it. That's not what we're doing in this work, but if that was the case, then we would need to design some kind of prompt that would more effectively handle the context.
Yeah, what I mean is that if your schema is generating these kind of full sentences,
Yeah.
and you're generating paraphrases on that,
Yeah.
GPT-3 will never create a paraphrase that is just one
Oh, I
sentence,
see.
right?
Okay.
If you don't provide the dialogue context.
Right. Yeah, that is a real concern. And I guess like the way to deal with it would be to modify the reformulation so the dialogue context is included in the prompt. Although I think that might be too difficult, or like with the limitations of the prompt, just because you'll be able to provide way less examples since the dialogue context will take up way more space. Yeah, I guess that is a real problem, and it's possible that our models that are trained on the synthetic data, that it doesn't have like these context dependent utterances, won't be able to handle that type of thing.
Okay, thank you.
Yeah, thank you.
Thanks, Shakib. This very cool idea. I need to think about it a little more. But one thing I often have trouble with is even when we get humans to do paraphrases from templates and come up with similar things, comparing that to real organic data, it's often biases things in odd ways and puts more importance on the things that people can easily think of to paraphrase, as opposed to the distribution that really comes up. So I was wondering if you thought that LAD has similar issues, or
Yeah, that's a great question. Certainly LAD has those issues. I don't think the data that is generated by LAD is by any means comparable to human data. I think if we look at, I'm not sure if I put this on the slide. I didn't, but I did do an experiment. I think this is in the paper, where we took GenSF, and rather than training it with all the data produced by LAD, we trained it on 64 utterances that were written by humans. And that outperformed this 50.9 number. And that just goes to show that the human data will always be better, even if there's issues like that. And like, we're not claiming that this data is good, just that it's sufficient to teach the model something. And the reason that this works, like my intuition here, is that large language models know something. They know something about the distributional structure of language. And by leveraging that, we're basically just getting around the fact that we can't train these language models directly. Yeah. Thank you.
Thanks, everybody. We're almost back on time. A few announcements. So we now go